Welcome to this tutorial where we'll be learning how to create a serverless API using Amazon Web Services and AWS CDK. In this tutorial, we'll be covering the following topics. First, we'll start with a brief introduction to AWS in general and what AWS CDK is. Then we'll be installing and configuring the AWS CLI, which is a requirement for working with CDK. Then we'll create our first AWS CDK app and deploy it. Afterwards, we'll proceed in creating our first API gateway using CDK. Then we'll make sure our API gateway is connected to AWS Lambda. Our Lambda will be reading information from DynamoDB. And finally, we'll take a look at how we can monitor our serverless API. So, without further delay, let's start with our first topic. Before we dig deeper into our application, we need to pause for a second and talk about what AWS is, because AWS is the backbone of our application. AWS is a set of services offered by Amazon. Amazon itself is a leading provider of cloud services, just like Google Cloud, Microsoft Azure, and DigitalOcean, for example. AWS specifically offers a lot of different products. We'll not go into detail of every single one of them. For the purposes of this example, we'll only focus on a couple of serverless products that AWS offers. In particular, API Gateway, Lambda, and DynamoDB. If you are interested to learn more about AWS and all of the other services that Amazon provides for software developers, feel free to visit aws.amazon.com. Now that we've covered AWS, it is time to dig deeper and understand a little bit more about AWS CDK as well, which will be the backbone of our tutorial. What is CDK actually? Well, AWS CDK stands for Amazon Web Services Cloud Development Kit, which is basically a framework for creating infrastructure as code. And infrastructure as code is quite popular nowadays because it allows us to define our infrastructure using familiar programming languages and gain some other benefits that we'll see in a second as well. Why do we need infrastructure as code in the first place? Well, it's simple. It allows us to document our infrastructure changes in time. Besides documenting our infrastructure using things like comments, proper variable names, and class names, it allows us to also version our infrastructure using familiar version control like Git or any other tool we want to use, just like our source code. Any change that we make to our infrastructure is now reversible, meaning that if our infrastructure as code is versioned, we could easily go back to a previous commit and redeploy, just like a time machine for our infrastructure. Additionally, if all of our infrastructure is defined as code, this means that our infrastructure can be easily replicated across different accounts, regions, or even for different clients. From a pure knowledge sharing perspective, infrastructure as code allows us to containerize a piece of knowledge into some sort of reusable module, or in the case of CDK, a construct, and share that construct with another team or even make it open source. Now that we've covered the benefits of having infrastructure as code in the first place, let's see what makes AWS CDK so unique. Why don't you just use a different framework for infrastructure as code? Well, first of all, AWS CDK is created and maintained by folks at AWS. This means that it is very well connected with AWS services, including the underlying CloudFormation service. Practically, from a risk management perspective, there should be zero risk that CDK will go away sometime soon. Also, with CDK, compared to other infrastructure as code frameworks out there, you are not locked to a single programming language. Instead, CDK provides a couple of options like TypeScript, JavaScript, Python, Java, C#, and Go, the last one being a bit experimental. If you go with something like TypeScript, which is quite popular nowadays for multiple purposes, you basically have the option to use the same programming language for all aspects of your app, including the backend, frontend, and infrastructure as code in this case. Having a Node.js app, for example, with TypeScript as a programming language, and also a front-end single-page application like Angular and React based on TypeScript again, will mean that your whole application is just written in TypeScript. Your developers will love you. And also CDK has very good TypeScript support, so this is usually the recommended path to go. This being said, let's dig deeper into our tutorial. Before we dig deeper into our application, we first need to install the AWS CLI and configure our credentials. This is required so that we can programmatically access our AWS account and create and manage resources like CloudFormation deployments, API gateways, Lambdas, CDK deployments, and so on. As of creating this tutorial, the latest available version of the CLI is v2. That's why I recommend you go ahead and install that version directly. Instructions for installing the CLI for various operating systems are already available inside the AWS documentation. In this video, I'll demonstrate how to install the AWS CLI on a Linux-based operating system, Ubuntu in my case. In order to install AWS CLI, we need to have the unzip and the curl package installed first. Now let's go ahead and install the AWS CLI. If you get this output, or one that is similar to this means that we are almost ready to go. We just need to configure our AWS credentials within the CLI. So after your first login to the AWS Management Console with the root account, good practices dictate that you should create an IAM user with administrative permissions for yourself and stop using the root account afterwards. This is what we'll do now. Let's first go to the IAM service of AWS. Let's create our administrative user. You can call it anything you like. We'll only be using the credentials of this user within the CLI, so we don't really need the password, but in the future you might have a need for it, so we are enabling it here. We need to give permissions to this user to manage this AWS account, so I'm attaching the policy called administrator access to this user directly. Now that we've created our IAM user, let's extract the credentials for it. By credentials, I'm referring to credentials that we'll use within the AWS CLI. Actually, what AWS CLI will use under the hood to programmatically access this AWS account. First of all, after we created our user, we already have a predefined access key, predefined credentials here, which will for now just deactivate and delete. Let's continue by creating a new access key that we'll use within the AWS CLI. Configuring the AWS CLI is pretty easy. You just need to run the AWS configure command. You should use the AWS access key ID and AWS secret key ID that you've taken from the AWS console. The region can be any one of the regions that AWS supports. Let's pick US East 1 for now. Now that we've configured the AWS CLI with our credentials, let's do a quick test to make sure that the CLI can communicate with our AWS account. Before I can use the CLI, I need to install a package called less, which is what the CLI is using to display useful output. Now let's run the actual test command I'm referring to. If you see an output similar to this means that the AWS CLI is properly configured with credentials, and you can use the CLI to operate with your AWS account. In the previous tutorial, we've learned how to configure the AWS CLI so it can effectively communicate with our AWS account. Now let's create a folder for our first AWS CDK application and navigate to that folder. Let's initialize a brand new CDK application using TypeScript as a base programming language. Of course, CDK also supports other languages, but for the purposes of this tutorial, we'll go with TypeScript. Now that we've created our CDK application, let's look at the basic folder structure. Every CDK app consists of, maybe you guessed it, the app, which is located within the bin folder. The app is instantiated like this, and then the app is composed of one or more CDK stacks that are attached to the app using the first parameter that is passed to the stack. The stack itself is usually located within the lib folder. In the next tutorial, we'll be defining the body of this stack, or actually defining the infrastructure of our application. In the previous tutorial, we've successfully created our first AWS CDK project, which consists of the CDK app and a single stack within that app, as you can see here. Now let's try deploying this CDK project to our AWS account. Before we do that, let's talk for a second about CloudFormation. What is CloudFormation exactly? CloudFormation is a service by AWS that allows us to define a YAML or a JSON file that defines our infrastructure. By passing that YAML or JSON file to the CloudFormation service, we are essentially telling AWS to create all the necessary infrastructure that we defined within that file. CDK takes advantage of CloudFormation internally, so we don't really need to know anything about CloudFormation at this point to work with CDK. So let's move forward and deploy our CDK application. Deploying a CDK application is usually as simple as running the npx cdk deploy command. Of course, in a more advanced scenario, you will need to add extra arguments to the CLI. For example, if you have multiple stacks within the CDK application. Now that our application has been deployed using CloudFormation as a service internally, we already talked about CloudFormation, let's see the final result of our deployment within the AWS Management Console. In order to see our deployed stack, we need to go to the CloudFormation service. I see here that the stack was successfully deployed. However, when we inspect it, we see that the only resource that is contained within this stack is actually some CDK metadata. That's because we haven't defined any actual infrastructure that we want to deploy using CDK. In the next tutorial, we'll be enriching this stack with using constructs here to create an API gateway. See you then. For now, our application is quite boring because it doesn't have any actual cloud resources that we provision using CDK. Let's change this by provisioning an API gateway using our CDK project. To provision any cloud resources using CDK, we first need to install the relevant package that holds the useful constructs that we want to use within our stacks. Usually, if you Google for AWS CDK followed by the service for which you want to provision some constructs, you'll end up on that exact npm package. In order to provision an API gateway using our stack, we first need to install this npm package. If you wanted to provision S3 buckets, Lambdas, or any other AWS services, there is almost certainly a package for that as well, as you can see from the documentation at the left side. The AWS CDK team is working really hard to combine all of these within a single package in version 2 of the CDK. Right now, as of creating this tutorial, the latest version is 1.119. Now that we've installed the API Gateway package that comes from CDK, we are ready to use constructs that come from that package. In order to use these constructs, we need to import the package itself. There are multiple options here. The most trivial one is to import the whole package using an alias. Now that we've imported the package within our file, we are ready to use the constructs that come with it. How we do it is by simply instantiating objects using standard object-oriented programming. Let's create a new REST API. Every construct within a CDK application is placed hierarchically within the CDK application. If you remember from the previous video, we placed the stack within our application by passing the application as first parameter to the stack. The same way, if we want to place this REST API construct within our stack, we need to pass the stack as a first parameter to the construct. We do this by using the this keyword in TypeScript. Almost every construct in CDK is composed, actually accepts 2 or 3 parameters. The first one is usually the context within the tree where we want to attach this construct within the hierarchy. The second one is a friendly name that we want to give to this construct. Let's call it API Gateway for now. The third parameter are the so-called props, which are different depending on which construct you are working with. For API Gateway, we might define stuff like course settings, logging, throttling, and so on. For other constructs, there are different props to define. For the purposes of our tutorial, we don't really need to define any advanced settings of our API Gateway. Let's try redeploying our application now, after saving the file, of course. You will notice that the deployment fails with a standard error. The REST API doesn't contain any methods. That's a validation error by the API Gateway service itself. You cannot create an API Gateway without defining any actual resources or methods within these resources. It cannot just exist as a placeholder, even from the AWS Management Console. So, in order to move forward, we need to define at least one resource and at least one method within our API Gateway. Let's do it now. In order to work with our API Gateway, I'll be assigning it to a variable. Assigning it to a variable, I get all sorts of properties and methods that I can use that come from the REST API construct. Specifically, I want to work with the root resource that comes by default with the REST API construct. The root resource, like any other resource within the API Gateway, exposes some utility methods like add resource, add proxy, add method, and so on. For now, let's just add a method called get. This will become a bit more interesting in the next tutorial. We see that adding a method to a resource in the API Gateway also exposes us to a few other options that we can pass, including the API Gateway integration target, which is the second parameter, and some extra options that we can configure here. For this point of the tutorial, we'll not be focusing on these yet. Let's try redeploying our CDK application one more time, now that we've added at least one method and at least one resource, which is the root resource. We see that CDK asks us for some IAM related confirmation, which is a standard behavior by CDK when we do IAM related changes within our deployment. And we didn't really create any resources that do IAM related changes. But CDK created these for us under the hood as we created the REST API and the resources and the methods. That's because most CDK constructs come with some sensible defaults and some predefined subconstructs being created automatically for us, just so our developer life is easy. And because of these IAM related changes, CDK is asking us for this extra confirmation. That's just good security. We see now that the CDK deployment is going smooth, which will result in our API gateway being deployed to our AWS account. After a few more seconds, we see that the CloudFormation stack has been now updated and our API gateway was successfully created within our AWS account. Let's go to the AWS Management Console and refresh our CloudFormation stack, just so we can see that the list of resources within this stack now includes the new resources that CDK created for us. If we go to the API Gateway service and inspect it, we see that the API Gateway is now provisioned here. In terms of resources and methods, it only has the root resource and the get method for that root resource, which is exactly what we defined in our infrastructure as code in the CDK part. As you can see, we didn't really care about defining all of the configuration needed to create a resource and a method. We just defined 2 lines of code. CDK takes care of the rest. In the next tutorial, we'll try to integrate our resources with a service called AWS Lambda, which is the business logic of our application. So far, we have created an API gateway, and that one is quite empty for now because it doesn't serve any purpose. We can see that it doesn't do anything by going to the AWS console, to the API gateway service, and let's try to extract the public URL for that API gateway and call it. One way to extract the API gateway URL is to click on that and go to the stages tab here at the left side, then expand the initial stage, which is called prod, any of the resources, and here you can find the URL to that API gateway. If we visit that right now, we get an internal server error, mostly because there is nothing that will handle that specific root URL. So let's try to fix that. Going back to our CDK code, here we can create a Lambda that will serve and handle any request to the root endpoint of the API gateway. Before we do that, just like we did for the API gateway, we need to install the relevant npm package. Provisioning Lambda requires this package called AWS Lambda, so let's install that to our project. The next step will be to connect this Lambda to one of the resources within this API gateway. To make this a bit more realistic, let's assume that our API will be handling creation, retrieval, updating of users. So in practice, our API needs to have a resource called users. Let's start by creating that one. We create resources within the API gateway at root by referring to the root resource first, and then we can call a method called other resource. The first parameter is the path parameter, which basically means what the URL will look like after the base URL of the API gateway. This is the base URL. What we want to expose within this API gateway is a URL called /users. So let's define our path parameter to be /users. And we can assign this to a variable called users resource. Now that we've created our resource, let's expose one or more HTTP methods within this resource. Let's start with the get method, which will be the listing of users within our application. So users resource,
So far so good, but we still don't have the business logic connected to this resource and this method. What will be actually handling these requests? What will be returning the response? In essence, we need the code, we need a place to write the code which will look into the database, read information or write information into the database. So within the AWS ecosystem, the most useful service for creating such business logic is naturally the AWS Lambda service. It's a way to create functions that live within the cloud. They scale without you having to do anything. Being serverless, you don't have to think about concurrency, load, and other similar topics for which you have to worry about if it's a traditional application. So with all these benefits of Lambda, let's try creating our first Lambda within our CDK project. Now that we've installed the package, the AWS Lambda package within our project, let's continue by importing that package within our stack. Of course, I don't recommend that you rewrite these imports every time I can. Just use the functionality of your integrated development environment. So, our Lambda for listing users, let's be explicit about variables naming for now. Let's call it Lambda list users. How do we create a Lambda? We refer to the Lambda package that we just imported above, and we create a construct called function. This construct is exposed by this npm package. As with the REST API construct, and as any other construct within the CDK ecosystem, this exposes three parameters. We forgot the keyword. This exposes three parameters. The scope, which is kind of a context, as I mentioned in the previous tutorial. Let's attach the Lambda to the current stack. So using this. The second is a friendly name for this construct that identifies it within the CDK hierarchy, within the CloudFormation hierarchy. Let's call it, again, Lambda list users. The only importance here is that it's unique within the hierarchy. And the third parameter are the props, or properties, or extra configuration for this construct. For the API gateway, or REST API construct that we used here, we didn't really need to utilize props, because out of the box the API gateway works pretty fine. It comes with useful, sensible defaults. However, for the Lambda function construct, we need to define at least the path to the Lambda source code, because here we are just defining that we want to create Lambda within our AWS account, but we still need to define other parameters like, as I said, where the source code lives within our file system, memory, timeout, and other configuration options are exposed using this props parameter here. After consulting the AWS Lambda construct library documentation, we see that the required parameters for creating a Lambda function are actually three. One is the code prop, which refers to the location where our Lambda source code lives in. The handler, which we'll cover in a second. The runtime actually tells the AWS Lambda service, what sort of environment to create as the runtime for our Lambda. So let's start by configuring our Lambda props here. First, let's define the runtime. Okay. The handler is a reference to the function, to the file, and the function that is the main entry point for our Lambda. In our case, we'll be naming our file index.js. So the file name is index, it's just index, we don't need to specify the extension. And then we put a dot as a separator. After the dot, we need to define the name of the exported function within that file that will be the entry point of our Lambda. The default in all examples online is called just handler. So to summarize, we need to have a file called index.js and an exported function called handler within that file. And the last required parameter for Lambda is the pointer to the code where our Lambda will live. So code. But it's something that comes from Node.js, so it's just imported. Okay, so to summarize, we are telling Lambda that our Lambda is living within a directory called Lambda handler, which is relative to the current files directory. Path join will simply concatenate the two paths. And from asset is basically bundling that directory within a zip file and passing it as the code parameter to Lambda. Let's move forward. Let's just first save the file, and let's move forward in creating our Lambda source code within this folder. First we create the folder, then we create the Lambda handler file, which we already defined here. The file needs to be called index.js, and we need to export a function called handler inside. Let's return a dummy value from our Lambda, which we'll start enriching later. And we'll get back to it in a second. Let's try deploying our CDK application. So it seems like we made a mistake here by defining the slash at the beginning of the path for users. This is a fairly common error that you always get when you start using CDK within a brand new AWS account, like we do in our tutorial. It's just telling us that we need to run the CDK bootstrap command one time for our AWS account, which will help CDK create some temporary resources within that AWS account to work with. These resources include an S3 bucket where CDK is putting some temporary assets, zip files, and so on before it can actually move forward with deploying them to our account afterwards. Let's just use the CDK bootstrap command to do it. Again, this is only a one-time operation. Now that we've bootstrapped our AWS account, let's try redeploying our application. If we inspect our API gateway now, we should see that there are new resources here within the hierarchy of API endpoints. The user's endpoint that we just created and the getHTTP method. When we inspect the getHTTP method, we still see that the integration type is mock here. That's because we haven't really connected our API gateway to the Lambda. We just created the Lambda. So if we go to the Lambda service, we should see this function that we provisioned using CDK. So basically these lines of code. Now let's try connecting our API gateway, resource, and HTTP method get with our Lambda. Or to put it simply, when a request is made to the user's endpoint using the HTTP method get, the Lambda will be invoked under the hood, and the response from that Lambda will be the response of that API call. The way to connect an API gateway, resource, and HTTP method to Lambda is using the following code. The Lambda integration class, in this case, is not a CDK construct, so the arguments that it receives are following a different structure. It only accepts one single required parameter, which is the Lambda handler. Given that we created it below, let's move this code a few lines below the Lambda function, so that we can use the Lambda function here as the first parameter. Now that we've connected the API gateway, resource, and HTTP method called get to our Lambda, let's try redeploying the CDK application.
Now let's try visiting the API gateway. More specifically, the user's resource that we just provisioned and the Lambda that backs it. We see that the response here matches exactly what we defined within the Lambda function, which we'll confirm in a second. Here is our Lambda function. Success true. Let's try changing it to false and redeploying our application, just to make sure that any change we do here within the Lambda is reflected to the API gateway immediately. Let's try visiting our API gateway one more time, and we see that the response is different now, success false instead of success true. Up until now, we've created an API gateway, we've created a Lambda, we've created a resource called users and an HTTP method get to access this resource, and a Lambda that will be invoked when we call that URL. Let's try cleaning up the code a bit to make it more readable. We no longer need the user's resource variable. We also don't need the get method at the root anymore. So within the API gateway root, we add a resource called users, which that resource specifically accessible using the getHTTP method, which internally invokes a Lambda integration, and this is the Lambda that will handle that request. The Lambda itself is located within the Lambda handler folder, within a file called index.js, which exposes a function called handler. The runtime will be Node.js version 12. In the next tutorial, we'll be looking at ways to connect our Lambda function to DynamoDB, which is the NoSQL database service offering by AWS. Just like API Gateway and Lambda, DynamoDB is completely serverless, meaning that you don't have to care about provisioning, scalability. See you then. Up until now, we've created our first AWS CDK project, which includes an API gateway with a single path called /users, which is callable using the HTTP method get. And when we call that API endpoint, actually we are invoking an AWS Lambda function. But that function is not doing anything useful right now. Today, we will connect our Lambda function to the AWS DynamoDB service. What is DynamoDB exactly? DynamoDB is a NoSQL service offered by AWS, and just like API Gateway and Lambda, it's also managed by AWS. It's serverless, meaning that it scales automatically, and it connects pretty well with AWS services. In order to connect our Lambda to a DynamoDB table, we first need to create that DynamoDB table. In order to create any resources using CDK, we already understood in previous tutorials that we first need to install the relevant npm package that introduces these constructs for us to use. With DynamoDB, the procedure is pretty much the same. We first need to install the DynamoDB construct library or npm package. Let's navigate to our project folder first and install the package. After we've installed our package, we are able to create our first DynamoDB table. In order to create our first DynamoDB table, we first need to import the npm package that we just installed. Now that we've imported it, we are able to use constructs that come from that package. Let's create a new DynamoDB table. The table is a standard construct that again accepts the three useful parameters. The first one is the construct to which we want to attach this table. In this case, it's the current stack. Then there is the friendly human readable ID. Let's just call it users, because the table will hold our users. And then there are props. For other constructs we've seen, like API Gateway for example, we've seen that the props is not really important, and you can create an API Gateway with the default empty props. But for DynamoDB, the situation is not the same. There is a required prop here that we need to define. Let's see what it is from the documentation. So, the only required prop in order to create a DynamoDB table is the partition key. If you want to learn more about partition keys and sort keys, I recommend that you read the Getting Started tutorials of DynamoDB. It's explained pretty well. But simply speaking, if you are familiar with SQL-based databases like MySQL or Postgres, the partition key is basically like a primary key of the table. It has a name, naturally, and it also has a type. We need to define the type of this column. It might be a string, number, and there was one more option that I don't remember now. So let's define our partition key while creating our DynamoDB table. Oops. Let's leave it ID for now because we are not interested in the structure of this table for the purposes of this tutorial. We'll just store like IDs and emails of our users. Now that we've defined the table construct, the DynamoDB table within our stack, we are ready to redeploy our application. While our application is being deployed, let's change a bit the source code of our Lambda. Let's make sure that this Lambda starts to read all the rows from within that DynamoDB table and returns them as a response, instead of just returning this object with success equals false. How do we read information from DynamoDB? Well, we can either use a query or a scan operation when we talk about DynamoDB. For the purposes of this tutorial, we will not be digging that much deeper into how DynamoDB works, so let's just use scan for now. The way to do DynamoDB operations, actually the way to communicate with any other AWS service from within a Lambda, the easiest possible way to approach this is to use the AWS SDK. Let's not confuse this with CDK, because CDK is the Cloud Development Kit of AWS, which is a way to create infrastructure as code, whereas the SDK is just a set of utility classes and functions that allow you to programmatically communicate with AWS APIs. The SDK is available in many programming languages, including for JavaScript. For us to be able to use the AWS SDK, we first need to install it within our package. The package is just called AWS SDK, naturally. Now that we've installed the package, we are ready to communicate with the DynamoDB service within our Lambda source code. In order to make our Lambda read from a DynamoDB table at runtime, whenever that Lambda is invoked, we need to first import the AWS SDK within our Lambda. We do it by assigning it to a variable and requiring the package. Then, within our Lambda, we are able to instantiate the DynamoDB utility class. With this utility class, or actually object in this case, we are able to call the many operations that are available to us using the DynamoDB service. For example, the scan operation. The scan operation itself requires a configuration object passed as a first parameter, and that configuration object, the only required key within it is the table name. We'll fill this in a second as our table name is created. As our table is created actually by CDK. Let's pause for a second and focus on this piece of code here, if it is enough to support our use case. Not really, because our function is based on async await. Feel free to read more about async await online and pause this video for a second. But to put it simply here, this just means that we are not interested in implementing any callbacks within our function. The flow of code will be top to bottom. There will be no promises involved, and also will not use .then. However, the scan function here by default requires a second parameter, which will be the callback function that will be invoked when DynamoDB returns the scanned information. Since we are not interested in this behavior, we can just simply call a promise function. We can chain the scan function with the promise function, which will modify the behavior of the scan function, and now it will just return a promise. However, in order to avoid calling .then on the result of that promise, we can just put the await keyword as a prefix. Now, the result of our operation can be assigned to a variable. Since we don't have our table name yet, let's check the AWS console, since we created the DynamoDB table and redeployed our CDK stack. The DynamoDB table should already be there. When we go to DynamoDB tables, we see that there is now a DynamoDB table that we can use within our infrastructure to read and write items. For now, we have no items here. Let's try putting this table name within our Lambda source code and redeploying our CDK application. Now that our application is redeployed, let's try refreshing our Lambda. We see that the Lambda fails, but what is the reason? What caused our Lambda to fail? If we go to the Lambda service, click on our Lambda and inspect the logs for our Lambda using CloudWatch, we should see an error here that says something along the lines of user blah blah is not authorized to do blah blah operation on a given resource. This is a standard IAM related error that you'll be encountering a lot if you work with AWS in general. A generic explanation of this would be that one entity doesn't have enough permissions to work with another entity. I know it's a bit abstract. To put it simply, the Lambda is trying to do an operation on the DynamoDB table, but the Lambda does not have sufficient permissions to do that operation. How do we give permissions to our Lambda to communicate with that DynamoDB table? In this case, to read something from that table. Well, it's fairly easy with CDK, because the CDK constructs actually like table and function and REST API and almost all of the CDK constructs, to be honest. They come with predefined methods that allow you to easily delegate permissions from one resource to another. In this case, we want to delegate permissions from our DynamoDB table to our Lambda. We want to allow our DynamoDB table to be readable by our Lambda. In order to do it, let's first assign our DynamoDB table from within our CDK app to a variable called table users. Now, this variable here exposes a couple of available utility methods like grant, full access, read data, read write data, stream, and so on. More information about the difference between these methods is available within the CDK documentation for DynamoDB. For our use case, we want the Lambda function for listing users to be able to scan the DynamoDB table, which is a read operation. So we want to grant to our Lambda the grant read data permission. And the parameter that we pass to the grant read data utility function is actually the entity that will need this permission. In this case, the Lambda. Let's try redeploying our app now. Now that we've redeployed our changes where we grant the Lambda permissions to read from our DynamoDB table for users, let's see what the behavior will be when we try to visit the API endpoint for listing users. We see now that the Lambda succeeds because we get the successful response. This means that our Lambda is now successfully able to scan the DynamoDB table. However, we haven't really utilized the result that is returned from our DynamoDB scan operation. Let's utilize the returned value from our DynamoDB scan operation and return it as the result of our API call to the user's endpoint. The REST variable here contains the raw response from the scan operation. The only useful thing that we need from within that raw object is the items array. We can assign it to items for now. Let's be explicit about our variable naming for the sake of example. Now, if we don't have any items, we can just return an error, like status code 404 body JSON stringify message no users. Of course, feel free to adapt this to your needs. However, when we do have some items returned from our DynamoDB table, some users, let's modify this successful response that we returned here. Instead of returning a JSON object with just one key, let's return a JSON object with a key called users. And that users object will be composed of our DynamoDB raw items mapped using the standard JavaScript function called map, which is basically a way to transform an array of one type of objects to an array of different type of objects. The map function accepts one single callback function, which in turn accepts as a first parameter the current element that's being iterated, and the returned value should be how we want to transform that object specifically. So we can use a utility function that's provided by AWS DynamoDB converter. It's called onMarshal. Pass the value, which will basically mean this whole piece of code here will mean I want to iterate the DynamoDB row items that were returned from the scan operation, and I want to transform them because every item is again a row object that is returned from DynamoDB. It's not really a simple JSON object that we can use as API response. That's why we are passing it through this onMarshal function, which is basically converting that complex DynamoDB object to a simple JSON object, like a key value object. Once you see the response of the API, it should make more sense. Let's save the file, and before we redeploy our application, let's go to the DynamoDB service and create one fake user, just for the sake of example. When we go to our table and items, we're able to create an item that has some ID, let's say 123. We can also append some extra attributes, let's say an email, that might be john@example.com. And when we save this item, now we have our first registered user within our system. When we redeploy our application with the updated source code that we have here, now that we have our Lambda, which is scanning the DynamoDB table, or basically reading all of the elements within that table, and it's transforming them to simple JSON objects, and we also granted our Lambda permissions to read data to the DynamoDB table. This should in practice mean that after our CDK deployment goes through successfully, we should be able to see the list of our users as API response here. Now that our CDK deployment has completed, let's try refreshing this page. And we see that our API is now returning a key called users, which is basically the list of users that we have within the DynamoDB table. Let's try creating another user just to make sure that we are on the right track. Email Larry example.com. When we refresh our API, we see that the new user is now returned as well. So within this tutorial, we've successfully created a new DynamoDB table, defined the partition key for that table. We've also granted permissions to our Lambda to read from the DynamoDB table, and we also changed the source code of our Lambda to read from that DynamoDB table. Before we wrap up this tutorial, let's just use good practices, and instead of hard coding values within our Lambda source code, because as you remember, we took this DynamoDB table name after we CDK deployed our application and after we extracted this table name from the DynamoDB console. Instead of doing that, and to give our application more flexibility in terms of if the DynamoDB table name changes for whatever reason, or we redeploy the application to another region, instead of wanting to go and change all of these hard-coded strings here, we want to pass this table name as an environment variable to our Lambda function at runtime. So how do we do that? Now that we have our DynamoDB table assigned to a variable called table users, and we have our Lambda called, and we have our Lambda assigned to a variable called Lambda list users, we are also able to provide environment variables to our Lambda using the environment object, which is a simple JSON object. We can pass something like table name users, which will refer to the table users variable dot table name. This will automatically make sure that CDK will take the dynamic table name of our DynamoDB table and pass it as an environment variable called table name users to our Lambda at runtime. And within our Lambda source code, instead of having this hard-coded string, we are now able to import an environment variable using Node.js standard source code, process.env, table name users. So whatever that environment name has, it will be passed as table name to our Lambda. Let's try redeploying our application and refreshing our API endpoint just to see that it works as it did before our change. We see that the API response is the same. In the next tutorial, we'll be looking at the basic ways to monitor our new serverless API. In our previous tutorials, we've successfully created a serverless API gateway that is backed by Lambda and DynamoDB. So far so good, but no application is as perfect as one that has perfect logging as well. Logging is necessary not just for the development phase where you want to debug the code that you are developing, but also for the production phase where your application might be logging useful information for you to analyze later, like how fast certain operations happen, if certain features are producing any bugs that you want to detect and act upon. So for this reason, in this tutorial, we'll be looking at ways how we can effectively monitor our application, how we can check the logs for our application, and so on. For our setup, we can enable logging at a couple of places. First, we can enable CloudWatch logs and X-Ray at the API Gateway stage. The API Gateway itself, let's try visiting our API Gateway that we deployed in a previous tutorial. This is our API Gateway. As you can see from the settings of the API Gateway, there is not really a place where we can enable any logging here. The place where we configure logging for an API Gateway is actually at the stage. Every API Gateway comes with one or more stages. By default, there is the prod stage, which stands for production, and as we click on that stage specifically, we can see that we can configure all sorts of parameters for our API Gateway stage. Let's focus on the logging, logs and tracing. We see that by default, CDK, whenever it creates an API Gateway for us, it doesn't enable any logging. Let's change this now by navigating to our CDK project and to the place where we created our API Gateway. We've already talked about the props for every CDK construct. For our API Gateway specifically, we haven't defined any props, but now is a good time to take advantage of this. Looking at the CDK documentation for API Gateway, and more specifically the access logging part, we see an example where we can easily enable logging by first creating a CloudWatch log group and then configuring the deploy options for our API Gateway. Let's do it now. In order to create a log group, we first need to install the CDK package for CloudWatch, as we did earlier with API Gateway, DynamoDB, and Lambda. The way I personally find the package to install, as I mentioned earlier, is to search for AWS CDK and the given package name. Usually this leads you either to the directly to the construct or the package name that exposes that construct. In our case, the package that we need to install is this one, AWS logs. Navigating to our CDK project, the way to install that package is through the npm install command, or npm-i for short. Now that we've installed the CloudWatch npm package for CDK, we are able to create a new log group by first importing the CloudWatch package, as we did multiple times now. AWS logs. Now that we've imported our package, we are ready to create our log group, which will contain the logs for our API gateway. Let's first talk about CloudWatch and the CloudWatch log groups. If we navigate to the CloudWatch service within AWS, this is a generic offering by AWS, and it provides multiple options for collecting metrics, logs, configuring alarms that will notify us when certain events happen. The CloudWatch service itself is quite important within the AWS ecosystem, and it's quite rich in terms of options that it provides to you. In our case, we'll be focusing only on the logs and the log groups functionality. So here we have some log groups already created for us. This is the one for the Lambda that we created as part of our CDK stack. Before we move forwards, let's create our log group for our API gateway now. As with any other CDK construct, we have three parameters that we can pass here to the constructor. One is the scope or the construct where we want to attach the log group. The second one is the human readable name, and also the props, which we don't really need in this case. So we are not defining them, we are not passing them. So this log group will be created as part of our CDK deployment if I were to run CDK deploy now. However, let's finish our setup first before we do it. We saw from the documentation that the way we configure logging for our API gateway is by using the deploy options property. It is an object that has other sub-properties. Access log destination is actually the place where we are passing our log group. There is also another parameter that's configured within the API gateway documentation, which is the access log format. The most common use case is to use the access log format JSON with standard fields, which basically includes some contextual information about every API gateway request within every log that is written to the log group. Let's stick to the defaults for now. From the documentation, we saw that for the access log destination property within the deploy options is actually accepting an object from the type log group log destination. So let's change our code a bit to support this example. Instead of passing directly the log group as we created it above, we just need to wrap it in this class. That class within its constructor is actually accepting the log group that we created. And these are the only changes that we need in order to enable logging within our API gateway. When we run CDK deploy, we should see that logging is now enabled for our API gateway. Now that our CDK deployment is completed, let's go back to the log group feature of CloudWatch. When we refresh, we should see a new log group now that is named API Gateway Logs, where our requests to our API Gateway will be logged. We'll be able to debug and monitor what happens. If we refresh our API Gateway request that we've used for testing prior in previous tutorials here, we should be able to see a new log here. Okay, after around 10 or 15 seconds, we see that a new log appeared within the log group, and if we open it, we see some standard information about the requests like the request ID, the IP of the client, the HTTP method, the status code that was returned to the client, and so on. This logging information is quite limited in terms of its power, what you can do with it. So the more powerful option for debugging our API is to enable logging at the Lambda level. Luckily, when we use the Lambda construct within CDK, as we did here, logging is already enabled for us. So every console log line that we put within our Lambda is actually already logging within a predefined log group that is created for this Lambda specifically. Let's do a quick experiment. Let's put a console log here that will log the raw event that is being passed by API Gateway to our Lambda. This event includes all sorts of metadata about the request, like request ID, timestamps, and so on, the IP of the client, but also useful information for debugging purposes like the HTTP method, the request payload, the query parameters, cookies, and stuff like that. Let's redeploy our application and make another request to our API gateway and inspect the logs for this Lambda, now that we've put the console log here. Okay, our CDK redeployment is successful, and if we go to the API Gateway service, go to the resource and more specifically the HTTP method that for which we want to debug the Lambda, we see here the configuration for this resource and for this HTTP method, like how is the request being handled, how is it being transferred to the integration, in this case the Lambda that we created and attached to this HTTP method, and then how the response is being passed back to the client. Let's go to this Lambda here at the far right side of the screen, so we can inspect the logs for this Lambda. Now we land on the standard screen for our Lambda, where we can see the source code that represents the Lambda along with other configuration for this Lambda. The interesting thing for this tutorial specifically is the monitoring part, where we can inspect all sorts of metrics for our Lambda, like invocation count, the duration, which means how long the Lambda took to complete, errors, throttling, and all sorts of other information that we can monitor as our application grows with our business. The logs specifically for our Lambda, the place where our console log is expected to be seen, are the CloudWatch log group for this Lambda. When we click that link, we are led directly to the log group that is for this Lambda specifically. We already see from our previous experiments that we already have some previous log streams. Let's clean these up for now, just to make a clear experiment. And after we refresh our API call to this endpoint using the getHTTP method, we should be able to see in a few seconds a new log being created here following our console log. Looking at the contents of this log, just a reminder that we logged the raw event that comes from the API gateway to our Lambda, and we can of course create our source code in a way that reacts based on this event, like analyzing the requests, the user that made this call only looking for information within the DynamoDB table based on this user, and so on and so on. But for now we are just logging this raw event, and let's look at the structure of this event. How is it logged within CloudWatch log group? As I mentioned earlier, we have all sorts of metadata about the request itself, like the resource, the path, HTTP method, headers, and so on and so on. All sorts of useful information here that we can use in the future for debugging purposes and figuring out bugs as our application grows. And this was a quick and easy introduction to monitoring our serverless API. See you in the future.
Thank you for attending this tutorial. If you like this video, don't forget to like and subscribe. And you can visit my website at junaid.com. See you in the next tutorial.